Our project is focused on the enzymatic breakdown and recycling of single-use plastic waste. So polyethylene terephthalate is one of the main components of plastic. It's formed through the condensation of ethylene glycol and terephthalic acid. And this here just shows one of the units of the polymer. 359 million tons of plastic are produced every year, with PET being the main component. How can we more efficiently recycle PET? So one way we can do this is by repurposing cutinase enzymes to hydrolyze PET. So cutinase is a hydrolase that can break ester bonds and therefore has the capability to break down PET polymers into the monomeric components of ethylene glycol and terephthalic acid. So here are some PET-ACE enzymes that have been already known, and our focus will be on leaf branch compost cutinase. This figure depicts an enzyme activity assay comparing the previously mentioned PET-ACE enzymes. The y-axis shows the specific activity of the enzyme, where milligrams TAEQ refers to equivalents of terephthalic acid produced. Part B is a detailed hydrolysis kinetic study for PF-PET depolymerization by LCC, as described in Part A. So the plateau observed in this kinetic study represents the lack of thermostability of LCC at 65 degrees Celsius, and overall LCC outperformed every other enzyme, being 33 times more efficient. In order to optimize enzyme activity, enzyme contact surface analysis was used in order to study the enzyme substrate binding interaction. By further understanding the binding interaction, targeted mutagenesis can be used to optimize catalytic efficiency. So the substrate binds in a hydrophobic groove at the catalytic site of LCC as shown. So 11 amino acid positions were identified and specifically targeted for mutagenesis. So these variants were all assayed and only 2 showed significant activity improvement. So the 2 that showed improvement over the wild type were I and W variants of the F243 position, where the y-axis shows gain of activity. Optimizing the enzyme thermostability is very important because the PET polymer becomes much less rigid at 65 degrees Celsius and allows the enzyme to much more easily access the ester bonds. So 2 approaches were taken to optimize thermostability, one being introduction of divalent metal binding sites, which is represented right here, and the other approach was to replace the divalent metal binding site with disulfide bonds. So the disulfide variant produced a 9.8 degrees Celsius increased melting temp, but showed a 28% decrease in activity compared to the wild type, LCC, which is shown in this graph here. Overall, this disulfide variant was further mutated to restore the lowered activity. So this mutagenesis resulted in 4 quadruple variants, which we will now talk about. Ultimately, these 4 quadruple variants retained specific activity that was similar to or higher than that of wild-type LCC, with improved melting temperatures ranging from plus 9.3 to plus 13.4 degrees Celsius. So part A of this figure depicts 1 milligram of LCC per gram of PET, where the optimal conditions are shown in part B of 3 milligrams of LCC per gram of PET and an achieved efficiency of 90% depolymerization. This study demonstrates that high-quality PET can be synthesized again from the products of this enzymatic breakdown. This eliminates the need for synthesizing virgin PET and can greatly reduce the need to produce plastics. So the optimized enzyme in this case achieved a 90% depolymerization